Hello everyone, I am Bireshwar Roy. I am currently pursuing my third year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this course, I will be discussing some previous year GATE physics questions and try to solve them with proper explanations. This question was asked from the GATE physics paper 2021. This is a MCQ type 1 mark question and this question is from the topic Electromagnetic Theory. The question is, a matter wave is represented by the wave function psi as a function of xyz t equals to a e to the power I 4x plus 3y plus 5z minus 10 pi t, where a is a constant. The unit vector representing the direction of propagation of this matter wave is, these are the four options we are given. So we have to choose the correct one, which basically representing the unit vector along the direction of propagation. So let us see the solution. So our matter wave is given by this equation. It is clear that this is a plane wave equation. Plane wave equation has the form psi as a function of xyz t equals to a e to the power I k dot r minus omega t, where k is the propagation vector or the wave vector of this wave, r vector is the position vector and omega is the angular frequency of this wave. In our case, k dot r equals to 4x plus 3y plus 5z, which is written here. Now, if we just expand this dot product, then we will get kxx plus kyy plus kzz equals to 4x plus 3y plus 5z. Now, we will compare individual component of this k from left side to right side. So, basically it will give kx equals to 4, ky equals to 3 and kz equals to 5. So our wave vector is 4x cap plus 3y cap plus 5z cap. Now in order to find a unit vector along this propagation vector, what we will do, we will take the magnitude of this k vector, then we will calculate the k vector divided by its magnitude, which will basically give 4x cap plus 3y cap plus 5z cap divided by root over 4 square plus 3 square plus 5 square. After simplification, we will get 4 by 5 root 2 x cap plus 3 by 5 root 2 y cap plus 1 by root 2 z cap. So among the four options, the first option, option A, is the correct answer, which is basically representing the unit vector along the direction of propagation of this matter wave. This question was asked in the GATE physics paper 2021. This is a MCQ type 1 mark question and the question was asked from the topic solid state physics. The question is, as shown in the figure, X-ray diffraction pattern is obtained from a diatomic chain of atoms P and Q. The diffraction condition is given by A cos theta equals to n lambda, where n is the order of the diffraction peak. Here, A is the lattice constant and lambda is the wavelength of the X-rays. Assume that atomic form factors and resolution of the instrument do not depend on theta. Then, the intensity of the diffraction peaks is option A, lower for even values of n when compared to odd values of n. Option B, lower for odd values of n when compared to even values of n. Option C, 0 for odd values of n. And the last option, option D, 0 for even values of n. So we have to choose the correct option. In order to solve this question, what we have to find is that the resultant scattered X-ray intensity on a particular plane as a function of the order of the diffraction peak. Let us see the solution. According to the question, we have to deal with this diatomic chain of atoms P and Q, where the distance between consecutive atoms P and Q is a by 2 and the lattice constant is a. If we look into this one-dimensional crystal structure carefully, then we can find that unit cell of this crystal structure will be this. This unit cell consists of two bases, that is P and Q. From now onwards, we will use only this unit cell for our future calculations. The diffraction condition is given by A cos theta equals to n lambda. Now we will multiply 2 pi by lambda on the both sides. So we will get 2 pi by lambda into A cos theta equals to 2 pi n. Now 2 pi by lambda is k naught, which is basically magnitude of incident X-ray wave vector. Our diffraction condition then becomes k naught A cos theta equals to 2 pi n. One more thing we have to consider, that is atomic form factor of the atoms P and Q. Now the atomic form factor or the atomic scattering factor is defined as amplitude of scattered X-ray radiation from an atom divided by amplitude of scattered X-ray radiation from an electron in that atom. So Fp is the atomic form factor of the atom P and Fq is the atomic form factor of the atom Q. Now consider this schematic diagram. So the X-ray radiation will incident on the atoms P and Q. The electric field of the incident radiation is given by E naught vector e to the power I k naught x, which is basically a plane wave equation. And then the X-ray will get scattered from P and Q. Here we will be considering only the scattering at an angle theta. Also we will assume a plane AB which is perpendicular to the scattered X-ray radiation from P and Q. After scattering from P atom, the X-ray beam will gain some extra phase due to the path length PC on the plane AB. Now the PCQ triangle is a right angle triangle. So PC is given by PQ times cos theta. Hence PC will be A cos theta by 2. So the extra phase gained by the scattered X-ray radiation from P atom will be k naught A cos theta by 2. Q atom is placed on the plane AB. So the scattered radiation will not effectively gain any phase on the plane AB. So resultant electric field of scattered X-ray radiation on the plane AB is given by Fp E naught vector e to the power I k naught x plus k naught A cos theta by 2 plus Fq E naught vector e to the power I k naught x. So first term is due to the X scattering from P atom and second term is due to the X scattering from Q atom. If we take E naught vector e to the power I k naught x as common, then we will get this. Now we will apply the diffraction condition, that is k naught A cos theta equals to 2 pi n. Then we will get ER vector equals to E naught vector e to the power I k naught x multiplied by Fp e to the power I n pi plus Fq. Therefore, the resultant intensity on the plane AB is given by IR proportional to electric field multiplied with its complex conjugate. So, IR proportional to E naught square into Fp e to the power minus n pi plus Fq multiplied with Fp e to the power I n pi plus Fq. If we just multiply these two terms, then we will get E naught square multiplied with Fp square plus Fq e to the power I n pi plus e to the power minus I n pi plus Fq square. Now from the complex number theory, we know e to the power I theta plus e to the power minus I theta equals to 2 cos theta. Applying that formula, we will get the resultant intensity is proportional to E naught square multiplied with Fp square plus Fq square plus 2 Fp cos n pi. Hence, we found the resultant intensity as a function of the order of diffraction. Here, two possibilities will come. One is for odd values of n and other one is for even values of n. For the first case, n equals to odd, this cos n pi equals to minus 1. Effectively, we will get IR proportional to E naught square multiplied with Fp square plus Fq square minus 2Fp Fq. So for n is equal to odd, it will be E naught square multiplied with Fp minus Fq whole square. Similarly, for n is equal to even value, cos n pi will be plus 1. Hence, we will get the resultant intensity for n is equal to even proportional to E naught square multiplied with Fp plus Fq whole square. Clearly, it has been seen that this resultant intensity for n is equal to odd less than the resultant intensity for n is equal to even. So among the four options, the option B is correct answer. So the option B is lower for odd values of n when compared to the even values of n. This is the correct answer for this question. This question is from the GATE Physics paper 2021. This is the MCQ type question having 1 mark. And the question was asked from the topic Electromagnetic Theory. The question is, consider a solenoid of length L and radius capital R, where capital R is very less than L. A steady current flows through the solenoid. The magnetic field is uniform inside the solenoid and zero outside. So this is the schematic we are given. Among the given options, choose the one that best represents the variation in the magnitude of the vector potential 0, Fi 0. These are the three components of the vector potential at z equals to L by 2 as a function of radial distance small r in the cylindrical coordinates. We are also given a useful information, that is curl of a vector in the cylindrical coordinates. So these are the four options which shows the variation of the vector potential at z equals to L by 2 as a function of radial distance small r. So we have to choose the correct option which represents the variation of vector potential as a function of small r correctly. So let us go to the solution part. So we'll consider a solenoid having radius capital R and length L, and the current is flowing through the solenoid along phi cap direction. The axis of the solenoid is along z cap direction, and as the current is flowing along the phi cap direction, so our magnetic field in the solenoid will also be along the z direction. It is also given the radius of the solenoid is very less than of its length. So basically it will be considered as a long solenoid. Now we know for a long solenoid the magnetic field inside the solenoid will be constant, and that is given by mu naught Ni z cap, where mu naught is the magnetic permeability in the vacuum and N is the number of turns per unit length and I is the current flowing through the solenoid. And in the outside region of the solenoid, the magnetic field will be 0. Now current is along phi cap direction. So eventually the vector potential will also be along phi cap direction. We have to find the vector potential. So basically expression for vector potential both inside the solenoid and outside the solenoid. Now we'll consider the first case, that is smaller less than radius of the solenoid. So this is basically the region inside the solenoid. For this we'll consider a circular path of radius smaller at position z equals to L by 2. We will calculate the closed path integral of vector potential along this circular boundary. Now this line integral can be written as surface integral of curl of the vector potential. And we know the curl of vector potential is basically our magnetic field. So it can be written as the surface integral of B vector. Now inside the solenoid the magnetic field is constant, and that is mu naught Ni. So we can easily calculate this surface integral as mu naught Ni multiplied by pi small r square, where pi r square is the area of the circular region. And also from the symmetry consideration, the vector potential will be same along the boundary. So we can calculate this line integral as mod of a vector multiplied by 2 pi r, where 2 pi r is the length of the circular boundary. So our vector potential at position smaller will be mu naught ni by 2 multiplied by smaller, and in the vector form it will be mu naught ni by 2 multiplied by r along the phi cap direction. Now we will consider the second case, that is smaller greater than radius of the solenoid. For this, we will consider a circular path having radius smaller at position z equals to L by 2. So now our small r is greater than capital R. We will do the same treatment, and for that we will take the closed path integral of the vector potential along the circular boundary. And we can write this line integral as a surface integral of the magnetic field. Now magnetic field inside the solenoid is constant, that is mu naught ni, but outside the solenoid the magnetic field is 0. So we will split this surface integral into two parts. So one is for inside the solenoid and other one is for outside the solenoid. For inside, the v vector is constant, that is mu naught ni, and the surface area will be pi capital R square. So this first part will be mu naught ni pi capital R square. But the second part, the B vector is 0, because outside the solenoid the magnetic field is 0. So eventually this second integral will give us 0. And for the line integral, closed path integral of the A vector, this will be mod of A multiplied by 2 pi r. So our vector potential will be mu naught ni capital R square by 2r, and in the vector form this will be mu naught ni capital R square by 2 small r along the phi cap direction. As of now, we have calculated the vector potential for both inside the solenoid and outside the solenoid. So if we see the expressions of vector potential, then the A phi is proportional to smaller for inside the solenoid, and it is proportional to 1 by smaller in outside of the solenoid. So if we plot this plot will look like this. So among the four options, this option C is representing the variation of the vector potential as a function of radial distance smaller correctly.